Okay, thanks so much for having me here to present some of the results from my PhD. And I must say that everyone's presentations has been very impressive so far. Okay, I'm going to talk to you about the reactivity of the adeninate anion, which is the deprotonated form of adenine. So adenine and its anion features in research of DNA, coordination polymers, and biologically active compounds. DNA itself is a supramolecular structure composed of 4 nuclear bases which interact through non-covalent interactions. Nature uses DNA to store, transmit, and replicate biological information. However, these processes can become disrupted and lead to mutations due to the presence of rare tautomeric and anionic forms of nuclear bases. And research has shown that these rare forms are stabilized by the coordination to metal cations. Adenine and its anion has multiple sites for metal coordination, and this has led them to be used to develop complex molecular architecture and coordination polymers and biometal organic frameworks. And these take advantage of the self-assembly and dynamic interactions that are present, which can be fine-tuned for the desirable properties of the material. Adenine and the anion have also been used to develop an array of active compounds against diseases such as HIV, multiple sclerosis, and cancer, just to name a few. And DNA itself, the nuclear bases, can have alkylation on them due to the presence of carcinogens. And with these two, much research has been dedicated to understanding the regioselectivity of alkylation on adenine and its anion at the various nitrogen atoms. However, as research grows for metal coordinated complexes of neutral adenine and its tautomers, there is limited knowledge in the stabilizing effect that metal cations have on the anionic forms. So in my PhD, a section of it, I focused on the ion pairing of the adeninate anion with sodium and potassium in DMSO solution. I also looked at the possible metal coordination sites. I then moved into how these aggregate in solution, and then I looked at the kinetics and thermodynamics of the alkylation. So just some background on the ion pairing. A lot of research has focused on the metal coordination of neutral adenine and its tautomers. For the dominant form of adenine, where the proton sits in the N9 position, there's chelation at the N7 and the N1. Through theoretical studies, they have suggested that the amino group undergoes a hybridization change from sp2 to sp3, rendering these structures relatively unstable or less likely to exist. More favorable is the coordination of metal cations to tautomeric forms, in which these forms actually become stabilized by the presence of the metal cation, which renders them more likely to exist in solution. So to obtain the adeninate anion, we treat adenine with equal amounts of base in alkane sodium and potassium hydride in DMSO solution, where hydrogen gas is given off as a byproduct. In solution, we'll either have ion pairs or solvent-separated ion pairs, or free ions in solution. And through UV spectroscopy, if you have an ion pair, you'll have an ion-dependent shift. So in our research, this is what we observed. We observed an ion-dependent shift of the UV band of the adeninate anion in the presence of the sodium and the potassium ion, where there's a blue shift when moving from the larger potassium at the 272 nanometer wavelength to 269 for the smaller sodium. And this is due to the sodium stabilizing the ground state to the larger extent as it has a larger cationic field strength. So we were interested in to see whether or not we could dissociate these ion pairs. And we did this by adding water into the study. And what we observed is that we had narrow, sharp, finger-like bands, which is due to the DMSO water metal counter-ion complex. And we also have a solvent-induced blue shift. We then wanted to see if we could actually observe the free adeninate anion, and we did this by adding large amounts of 15 crown 5 ether for the sodium or 18 crown 6 ether for the potassium. and we observed the exact same absorption profile, 262 nanometers, which was the free adeninate anion. So we also studied this with NMR spectroscopy, where again we observed an ion-dependent chemical shift, depending on the sodium and the potassium. And based on the chemical shifts of the carbon NMR, we could predict where the counter-ion was coordinated. And we said it was most likely in a unidentate or bidentate fashion at the N3 or N9 nitrogen atoms of the purine ring. This was supported partially by the crystal structure that was obtained that showed metal coordination at the N9 position, but also at the N1 and the N7. Unlike the UV spectroscopy study where we had over 100 equivalents of the crown ether present, in our NMR study for the potassium adduct, we only had 1.2 equivalents of the crown ether present, in which there was a downfield shift. And this, to us, actually suggested that the crown ether was coordinating to the potassium adduct rather than removing the counter ion. And this was supported by the crystal structures where we see the crown ether simultaneously coordinating with the potassium and the adenine. And but more important, we see that there is a bidentate coordination at the N3 and N9 atoms, which led us to believe that this is probably the site where this metal is coordinating in solution. However, we can't determine the exact site of metal coordination through NMR and UV spectroscopy studies, so we turn to theoretical studies. And we modeled several isomers where the metal is coordinated in plane at the nitrogen atoms, out of plane at the amino group, or through a cation-pi interaction. And we wanted to understand the main driving factors of these interactions. So we looked at the difference in relative energies. We also looked if there was localization of the negative charge on the free adeninate anion that would perhaps attract the counter ion to a specific site. We also wanted to see how the system responds to metal coordination and the dominating interactions which govern complexation. And we did this at the superior CCSD level theory, but also at the more achievable DFT level theory. So these were the isomers which we investigated that were obtained at the CCSD level theory, and the same were recovered at the DFT. And from here, what I wanted to point out was that the potassium results in fewer isomers. And this is because the potassium, which is larger in size, can only coordinate in a bidentate fashion at the N9 and N3 position, where the sodium can occupy these sites as unique isomers. And also potassium is not involved in a cation-pi interaction, unlike the sodium. Unlike previous studies, which suggested that the metal coordination at the N1 and N7 sites would lead to a change in hybridization of the amino group, this is not observed. In our theoretical studies, the amino group retains its trigonal planar geometry. So looking at the relative energies, we can see for the coordination of the endopurine ring nitrogen atoms that there's not much difference. This is replicated in the Gibbs free energy, and this falls within calculation error. So this means that all of these have equal probability to exist in solution. However, looking at relative energies is like looking at the tip of an iceberg, and you only get one aspect of the system. In our research group, we like to dig a little bit deeper and see how the system responds to changes such as metal ion coordination. And we do this partly by looking at the change in net atomic charge and the change in intra and intermolecular interaction energies due to changes in the immediate or distant molecular environment. And from this, we would gain a better understanding of the system, and perhaps this would indicate where the metal counter-ion is most likely to exist. So first, we're going to have a look at the net atomic charge of the free adeninate anion prior metal coordination. And we see that the endopurine ring nitrogens all bear similar charge. So this indicates to us that as the counter-ion would approach, there wouldn't be an immediate area that it would be attracted to in one of these nitrogen atoms. Moving to how the system changes when the metal ion actually coordinates, we see that there's charge polarization of the adenine ring, where the nitrogens that are involved in the coordination gain a lot of negative charge. This is less so for the potassium ion, as the sodium perturbs the electronic environment to a large extent. And there's equal charge transfer between the adeninate anion and the sodium and the potassium ion, regardless of the difference in perturbation of the electronic system. And this is highest for the N3 and N9 isomer. So we decided to look at how the adeninate anion changes in regard when a metal ion coordinates. And what we see is that the system is highly stabilized when the metal ion coordinates. Whereas when the coordination to the N10, the system becomes highly destabilized. We then look at the ionic bond itself, and from this we can see that the formation of the ionic bond is highly favorable for all of the isomers, and for the entire system as a whole. We see that the entire system is stabilized upon metal ion coordination, but mostly for the coordination at the bottom of the purine ring at the N9 and N3 positions. And this supported our experimental finding that the N9 and the N3 would be the most likely site of metal coordination, and our theoretical studies suggest that it's most likely in a bidentate fashion. So we wanted to look at the self-aggregation of these ion pairs. And since Watson and Crick has proposed the structure of DNA, a lot of researchers went into studying the non-covalent interactions in order to understand their function in structure, in their role in structure, function, and stability. And a lot of research has focused on the self and heteroassociation of adenine, as well as the effect of substituents on these non-covalent interactions. A lot of these studies are done through NMR and UV spectroscopy, in which the solvent determines the mode of aggregation. In water, pi-pi stacking is the dominant interaction for adenine dimers, where the protons experience a shielding effect due to the ring current experienced on the neighboring molecule. Whereas in chloroform, we have hydrogen bonding interactions between adenine molecules, where the proton involved shows a de-shielding effect. So we used these trends in shifts to study our adenine salts in DMSO solution. So first I wanted to point out the visual difference between the sodium and potassium adducts with increasing concentration, where the potassium adduct showed a distinct yellow color as the concentration was increased. When we have a look at the change in shift with increasing concentrations, there are two distinct regions for both the sodium and potassium adducts. At the lower concentrations, we have a shielding effect, which is in line with the formation of pi-pi stacked dimers. However, at higher concentrations, the protons then move downfield, which have a de-shielding effect, which we would expect for the formation of hydrogen bonds. However, the NH2 group, the chemical shift for the NH2 group of the potassium adduct is absent, which made its interpretation a bit more difficult. But in the crystal structure, it is there, it's just not showing inside the NMR spectrum. So we used thermodynamics actually to investigate the type of aggregation that was happening at these higher concentrations. Research has shown that adenine usually coordinates through cyclic hydrogen bond formation, which has an enthalpy of formation around 12 to 16 kilojoule per mole and an entropy of minus 145 joule per mole Kelvin. And from our thermodynamic studies, what we have observed is that the change in enthalpy is significantly lower, which would suggest to us that we don't have cyclic hydrogen bond formation. And also our entropy was quite lower, which would indicate that we had a lot of liberation of solvent and perhaps a gain in vibrational entropy from a weak hydrogen bond. So from this, we actually deduced that our aggregates could be forming through coordination of the counter ion with the presence of maybe a weak hydrogen bond. So now that we started to gain an understanding of our system and accept that we had ion pairs that aggregate in solution, we had one aim left, which was to understand the kinetics and the thermodynamics of alkylating the adeninate anion. So previously in other studies, and also in our previous studies, direct alkylation of adenine yields a complicated yield mixture of regioisomers, which leads to the frustrating task of purification. So previous research has focused on the factors governing the alkylation, and they have shown that the nucleophilicity of the heteroatom, structure of the electrophile, nature of the leaving group, as well as solvent and product stability all plays a role. Previous research has focused on the product ratio at the endpoint reaction, in which the presence of different cations as well as different alkylating groups were investigated. From here, it was actually concluded that no ion pairs exist in solution, as the presence of different ions didn't result in a difference in the product ratio between the regioisomers, and very little change was observed with the use of different alkylating reagents. However, no kinetic or thermodynamic data has been reported for such reactions, and this is where we have focused. So we studied the alkylation of the adeninate anion, which we now know is an ion pair, in DMSO solution with the use of benzyl chloride. The N7 regioisomer concentration was too low to measure accurately, so we didn't carry out any kinetic studies for this regioisomer, and we focused mainly on the N3 and the N7. The N3 and the N9, in which the rate constant ratio for the N9 is 2.5 times larger than that of the N3. If we look at the dynamic NMR spectrum, in the early stages, we notice a slight migration for the N3. For these studies, it was carried out at 6 millimolar, in which we noted from the aggregation studies that this is the concentration in which we begin to notice a change in the aggregation mode. So this shift we attributed perhaps to a dissociation of the aggregates or perhaps the counterion. Did aggregation influence the kinetics? Yes, it did. And we observed this in the concentration-dependent studies of the adeninate salt, where it deviates from linearity at high concentrations. However, at low concentrations, we were near to first order, and this is then where we stayed for our thermodynamic studies. Overall, the second reaction was second order, which is what is expected for an SN2 reaction. So for our thermodynamic studies, we kept in mind that we're dealing with the ion pair, where the sodium counterion is most likely bidentate, coordinated through a bidentate fashion at the N3 and N9 position, which resulted in the charge polarization, pulling negative charge to these two sites, rendering them more nucleophilic for the reaction. And so it would make sense that these were the two main isomers that are formed. And we wanted to investigate how do these differ in the thermochemistries and the kinetics. So it was very interesting to see that the N9 actually had a higher enthalpy of activation as well as an activation energy than the minor N3 regioisomer. However, this was largely compensated for by an increase in entropy of the system, or less decrease in entropy of the system. And if you wanted to visualize this, we can see it by considering the well of the transition state region, where the N9 would have a gradual wide well in which the pathways leading to the N9 transition state with sufficient energy would pass through. For the N3 pathway, however, the well would be narrow, which would result in an entropic bottleneck. This leads to an overall Gibbs free energy of formation in favor of the N9, being 2 kilojoules per mole lower, which results in a 2.5 favor of the rate constant, which is what we observe. So understanding the adeninate anion and how does this research come into play? The first thing is that we actually understand our reagent that we are working with in the synthesis of biologically active compounds that use the adeninate anion in DMSO solution are actually dealing with the adeninate salt, in which the coordination of the counterion directs the alkylation. This led us maybe to believe that if you use different solvents, that would perhaps dissociate the ion pair formation or result in different coordination site, you can actually alter the nucleophilic sites and change the regioisomer ratios. And maybe if we use a different metal counterion, this would have a catalytic function when synthesizing biologically active compounds. Also, we know that aggregates influence the kinetics, so the concentration needs to be kept in mind. And our thermodynamics helps us contribute towards the role in industry to have better control of the synthesis and the development of new materials and synthetic routes. So I would just like to say thank you for all your attention, and thank you to my supervisors during my PhD, and for having me to present my work here. And I look forward to your questions.